There are two important things that students should remember. Say I have a uniformly charged shell. Total charge is Q and it is uniformly spread. So what will be the electric field inside at a point, say P, this shell? That will be equal to 0. Always remember this. This is very important and it will have a lot of applications. An electric field outside a uniformly charged shell is equal to 1 by 4 pi epsilon naught Q by R square, where R, so say this is a point. So R is distance from that point to the center of the shell, which means a uniformly charged shell for a point outside, like for say R greater than the radius R, behaves like a point charge placed at its center. So
Okay. And for what is the value of electric field if R is equal to the radius of the shell?
So when R is equal to radius of the shell, it is still the same. Then you will apply E is equal to 1 by 4 pi epsilon naught Q by R square.
Okay, so that result is for R greater than or equal to capital R. Okay. Okay.
Now let us study lines of force. Lines of force, it is a representation of electric field basically. So what are its properties? So tangent at a point gives field direction. So if it is like this line, so at this point the tangent is like this. So this is the field direction.
Okay.
Two lines do not cross each other. There can't be two field lines like this, because at this point you can't draw a tangent.
Okay. Like
Where will the electric field
like they can't be two directions for electric field.
it makes no sense.
Okay.
It is always directed from positive charge to negative charge. So suppose there is a charge Q and there is a charge minus Q. So it will be like this.
Okay.
And yeah, relative density of field lines is proportional to relative strengths of electric fields. Say this is the field line. These are the field lines. So we consider this area infinitesimally small area. So electric field in that area and another area here.
Okay.
So to calculate, to know exactly which is stronger, which is weaker, the relative density of field lines gives us the estimate. So since here the density is less, the field lines are more dispersed. Electric field here is less at this point.
Okay. Yes.
Field at this place is more.
Okay, so if the electric field lines are like more concentrated, that means the magnitude of electric field is more at that point.
And that is why you will get high electric fields near the point charge, because all the lines are originating like this. So if you see here, the electric field will be more. So at a far off distance, the field lines will be very dispersed.
Yes.
So electric field there will be less.
Yes.
Electrostatic potential energy. See, it is the work done in bringing a charge from infinity to the given point under their electrostatic influence. There is a charge Q1 and a charge Q2.
Okay.
Let us assume Q1 to be fixed. Q2 is brought from infinity to distance r.
Okay.
So the work done in doing so, that is stored as internal potential energy, not internal, potential energy of this system.
Okay.
And it is equal to 1 by 4 pi epsilon naught Q1 Q2 by R.
Okay.
Okay. So remember that since potential energy is a scalar, if you have to calculate potential energy of a system of say 3 point charges Q1, Q2 and Q3, then you have to calculate individual potential energies and then add up.
Okay, like we always have to calculate potential energy in pairs.
Pairs of two.
Okay.
Point charges.
Okay.
electrostatic potential. See, electrostatic potential is defined at a point due to a charge. So there is a charge Q. So because of its electric field, each point we can define electrostatic potential.
Okay.
Say V. So what is it exactly? Value V is equal to U by Q2. इसका मतलब ये हुआ कि it is potential energy per unit charge बोल ये कह सकते हैं.
Per unit charge.
हाँ. Potential energy of unit charge. So Q2 अगर 1 coulomb
Okay, like if in this case, in the previous case, if Q2 is equal to 1, okay, then okay.
Electrostatic potential and electrostatic potential energy are same.
Okay, so like the same we do it in the case of electric field. Like if we wanted to calculate the electric field, so we did the charge Q2 as 1. Okay.
So since exactly, so F by Q2 is equal to E. So similarly, U by Q2 is equal to V.
Okay.
So this remember.
Okay.
And the formula will be V is equal to 1 by 4 by epsilon naught Q1 by R.
Yes.
So there are 2 points A and B, and at those 2 points, potentials are defined VA and VB.
Okay.
Then potential difference VAB is equal to VA minus VB simply.
Sir, can you tell us, like, if there are 2 points, if there are 2 charges, okay, and there is a single point, so how do you find the resultant electrostatic potential? Like, can we just add them up?
Exactly. Since I mentioned here that it is a scalar, it is a scalar, which means there are say 2 charges Q1 and Q2.
Okay.
So electric potential at this point, say P, Vp will be summation of electric potentials due to Q1 and Q2, and that is not a vector summation, that is a simple summation.
Okay, just a scalar quantities. Okay.
The electric field E bar and electric potential V are related at a point, and it is given by this relation. E bar is equal to negative of gradient of V. So what exactly is this? It is equal to minus of dou V by dou X I cap plus dou V by dou Y J cap plus dou V by dou Z K cap. When I say dou V by dou X, I mean partial differentiation of the potential function with respect to X. Similarly, this is with respect to Y, this is with respect to
Z.
Okay. So for equilibrium condition, what we know is net force on it should be is equal to 0. So if force is equal to 0, that means electric field is equal to 0.
Yes.
And from that, using this, we can conclude if something is in equilibrium, then dou U by dou X
is
equal to 0, dou U by dou Y.
So all three must should be 0.
Exactly.
And in the previous equation we used V, and now in this equation we are using U.
Okay. Since we know that V is equal to U by Q2 from what we learned.
Okay. Yes.
So
yes.
They are directly proportional.
Okay, we can use both V and U in this case. Yes.
See, if the potential at a point is 3 and a charge of 2 coulomb is placed there,
then the
potential energy will be
6. Okay.
So it will always be proportional to this. So if this is 0, then it also implies
that dV by dx, del V by del x is also equal to 0.
Exactly.
Okay.
So this equation is also very important. This is the same as this equation in a different form. It says delta VAB is equal to negative of integration from RA to RB E bar dot dr.
Okay.
So what exactly, how to interpret this is, say there are 2 points A and B.
Yes.
So we want to find the potential difference between these 2 points, that is VA minus VB.
VB.
So what we need to do is we need to travel along this path and integrate this particular quantity.
Okay.
We will find the value of VA minus VB.
So at a particular point O between AB, we have to use vector E and vector dr at that instant, and take the dot product and then integrate it to find VA minus BB.
Exactly. So there is one thing you should notice here, that it is independent of the path. See, because VA is defined for a particular point, VB
Yes.
is defined for a particular point,
Yes.
which means VA minus VB is defined for 2 points.
2 points. Yes.
So if this is defined for 2 points, so this quantity can also not vary because of dr. So if I travel along this path or this path or this path,
So for all paths, integral of E dot dr should be same.
it should be same.
Okay.
This is the case for conservative forces.
Yes. Yes. Yes.
So you can relate to that.
Okay.
So what are equipotential surfaces? As the name suggests, equipotential means same potential, equal potential.
Yes.
So whenever you have surfaces at equal potential, then if you travel along it, like between any 2 points, gradient of V will be equal to 0,
Yes.
since equipotential.
Yes. Same potential.
So gradient V is equal to 0, which means E bar is equal to 0,
Yes.
which means if there is a equipotential surface, so E bar, there will be no electric field in a equipotential surface.
Electric field will be zero at all points,
At all points
on the surface.
On the surface.
Okay.
Okay. Now let us study electric dipole. Electric dipole is simply 2 point charges of opposite charges, as in Q and minus Q, placed at a distance 2a.
Yes.
Okay. So the dipole moment of that system is defined as P bar is equal to Q into 2a bar. Now A is from negative to positive, as in this.
Okay.
So P bar is also in the same direction.
Okay.
Electric field due to a dipole at a point lying on, let us calculate first, axial line. Axial line in the sense, the line joining minus Q and Q is called the axis line.
Okay.
So for a point lying on the axial line at a far off distance, that is R is much greater than A, that is equal to E bar is equal to K 2P bar by R cube. K is equal to 1 by 4 pi epsilon naught.
Yes.
And V is equal to Kp by R square.
Yes.
And remember that for a dipole, E bar is inversely proportional to R cube, because P itself already has one length, vector A,
Okay.
and V is equal to Kp by R cube, R square, sorry.
Okay.
And equatorial, for an equatorial line, that is, say if this is minus Q, this is plus Q, this is the equatorial line. So for that, E bar is equal to minus Kp bar by R cube, and V is equal to 0. V is equal to 0 can simply be concluded from the fact that it is equidistant from both charges, and one charge will impart a positive potential and one charge will impart a negative potential, and both will be equal, so they'll cancel out.
Yes.
And V is equal to 0.
Okay.
Electric field at a point r comma theta. मान लो dipole is placed like this, and we need to find electric field at a point P which is at an angle theta defined like this and a distance r. So for that, this is the formula. ER is equal to 1 by 4 pi epsilon naught 2 P bar cos theta by r cube, and E bar ER is along the line joining center and the point, and E theta is equal to 1 by 4 pi epsilon naught P sin theta by r cube, and it is perpendicular to ER.
Okay, but how do we why do we write P cos theta and P sin theta here?
Why do you write P cos theta and
P sin theta here?
See, for this I have to show you the derivation.
Okay, derivation. Okay, I mean, did you resolve the dipole moment of the did you resolve the dipole moment in two directions?
Exactly. That is how actually we calculate it. Say, if this is the from negative to positive, this is P, and since this is theta, so this is P cos theta.
Okay.
This is P cos theta.
Yes.
And similarly, this actually is P sin theta. So
yes.
In magnitude, this comes up.
Because along the equatorial, it is negative, like minus P. Minus P comes.
Instead of this, we have this.
Okay. So like in equatorial, the formula is 2 kp by r cube. So here P is equal to P cos theta, and so we get ER is equal to 2P cos theta by r cube.
Exactly.
Okay, and same for E theta, because equatorial it is kp by r cube and P is P sin theta.
Yes, correct.
Okay.
Let us move on to torque of a dipole. See, when dipole minus Q and Q is placed in an electric field at an angle theta, then torque experienced by it will be equal to P bar cross E bar, which is equal to P E sin theta.
Okay.
And the potential energy will be equal to minus P bar dot E bar, is equal to minus P cos theta.
Okay.
So remember these formulas.
Yes.
Let us move on to the next thing, flux. Flux is a measure of number of field lines crossing a surface. So it is equal to, flux phi is equal to E bar dot A bar. Say suppose there is a surface and field lines are crossing. So, and field lines are crossing perpendicular to the surface. So
Okay.
A vector, as you know from 3D geometry, is always perpendicular to the surface. So E bar dot A bar is simply E into A.
Okay, so A bar is the vector that is perpendicular to the surface.
Yes.
Okay.
And so, exactly. So if there is a surface like this placed in electric fields which are parallel to the surface,
Okay.
then E dot A will become 0.
Okay. Yes. Yes, because A is perpendicular to the surface and E is along the surface, so E dot A will be equal to 0.
Cos theta is equal to 0.
Okay.
Dot product.
Yes.
So what is Gauss theorem? Gauss theorem says that closed integral of E dot ds is equal to summation of Q Q as in charge enclosed by epsilon naught. This is a very important formula. This closed interval means that the surface should be a closed one. It cannot be like the example I gave like this. It should be like a shell
Okay.
or a rectangle, a cuboid, not a rectangle, a cuboid, something like that.
Okay.
So Q enclosed means, see, how to apply this? There's a charge Q. So we make a Gaussian surface, a shell
Okay.
of radius r, and we apply this formula here. So E dot ds is equal to 4 pi r square.
Total area. Yes.
Total area of this surface.
Yes.
And from at every point,
Is
area and E are parallel.
yes. E dot A is EA.
So E into 4 pi r square is equal to charge enclosed is Q by epsilon naught. From this we can prove E is equal to 1 by 4 pi epsilon naught Q by r square, which is actually another form of Coulomb's law.
Yes. Okay, so like we can use Gauss theorem to derive the electric field of various charge distributions.
Yeah, and it is very useful for certain cases, as I'll show you. Say for a sphere of a uniformly charged non-conducting sphere. For that, the E bar will be equal to K QR by capital R cube for R less than capital R. See, this is capital R and this is small r, and this is the point P of our interest. And this is the center O.
Okay.
So charge at this point, we can derive this simply by drawing a Gaussian surface here.
Okay.
And for a point outside, draw a Gaussian surface and we get KQ by R square, which is almost as if placing all the charge at center. For a shell, same thing. Since for the Gaussian surface, Q enclosed will be 0. When small r is less than capital R,
Yes,
E bar is equal to 0.
Okay.
And when it is greater than or equal to capital R, E bar is equal to KQ by R square.
Yes, because total charge enclosed is Q, capital Q.
Exactly.
Okay. So like students, like we gave you the brief idea of how to apply the Gauss theorem, so you can apply it in different areas, like in the case of non-conducting spheres. So to find so it is an exercise that you have to find the value of E, and it should come out to be KQ R by R cube.
You can try out yourselves and match the answers. For an infinite sheet, an infinite sheet of areal charge density sigma. Areal charge density is charge per unit area is sigma. For that it will be sigma by epsilon naught simply, and it is irrespective of the distance of the point.
Okay.
It is a very interesting observation that it is irrespective of the distance, and this we'll be using later in capacitance. So what is a capacitor?
So in the previous case, in the infinite sheet, what was the direction of the electric field?
In the infinite sheet, the direction of the electric field is away from the point. So the point is here, then this is, and it is perpendicular to the area.
Yes, that is along the area vector or perpendicular to the surface.
Parallel to the area vector and perpendicular to
surface. Okay.
If it is here, then E bar will be like this.
Okay.
So say suppose I have a metallic body, and I have given it a charge Q.
Okay.
So all the charge will reside on the surface, and we know that surface will be an equipotential surface.
Okay.
Exactly. So we have found that Q is always proportional to V of the surface.
Yes.
So from this, Q is equal to CV. We can write it like this, where C is the capacitance.
Yes.
And capacitance, the units of capacitance is farad.
Okay.
Energy of a capacitor is equal to Q square by 2C. So you can apply it in this body.
So these are some simple basic formulas that you will figure out.
Parallel plate capacitor, as in two infinite plates are there. Then for those plates, capacitance C is equal to epsilon naught A by D, where D is the distance between them, and A is the area of the plates. Actually, they are not infinite plates. It is such that A is much greater than D. As in, dimensions of A are much greater than D. So
as compared to D, A is very high, but A can be anything like this. So
when under this situation, we can consider that all the electric field lines are like this,
okay,
and the boundary conditions can be ignored.
okay,
So for parallel plates capacitors placed in a series combination in a circuit like this is how a capacitor is shown. The effective capacitance is simply 1 by C is equal to 1 by C1 plus 1 by C2, and for parallel it is C is equal to C1 plus C2. This is reverse of resistors.
okay. So can you please show us what were the boundary conditions in the capacitor? Like what were the problems that we having in the boundary conditions? Like you said that A must be greater than much greater than D.
Exactly. Say so this is your parallel plate capacitor.
Okay.
So in the boundaries, it will not be always like this. Electric field will differ.
Okay.
So for such conditions, we have ignored such things since A is much greater than D. So we have ignored these effects. We have only considered that this is how the electric field is.
Okay, because A is very high, so that thing we can ignore.
Exactly.
Okay.